Hello everyone, this is the project presentation for AC591. I am Shihabuddin Ahmed and I'll be presenting real-time mobile net SSD detectors performance and enhancement and analysis for mobile device inferencing. In the past decade, most of the machine learning algorithm and architecture was fully dependent on the devices with high computational power for training. But with the emergence of embedded microcontrollers like Raspberry Pi, Tinkerboard, Jetson Nano, it has been possible to implement those machine learning model into more compact version, which can be used later on into different fields of technologies like home automation, robotics, computer visions, and autonomous vehicles and security, etc. These projects involve pruning an existing network, quantizing, optimizing, training, and converting in order to fit the large model for mobile devices like Jetson Nano. So TensorFlow Keras API was used to code the full network for us. The first step of the project was to train the model. So initially, I tried to began to train with the model with a Jetson Nano, but unfortunately I couldn't because the Jetson Nano could handle only a batch size of 2 images of 300 by 300 size, and it took around 4 seconds to complete each to process one image. So if there was like 1000 of images, it would take around 1 hour to complete for one epoch, which is not viable. So the solution was to train the model into higher computing devices. In this case, I use my own personal computer and then convert the then implement that trained model into Jetson Nano and see the performance. So this is the workflow of the full project. So this portion is the data portion. So the first step was the collecting the data for our model. We use the Microsoft Cocoa 2017 data. Then we pre-process. Then I pre-process the data and send it to 2 different models. So these are model built with TensorFlow Keras API. Both of these model are identical, but the only difference is being this left model uses a float point precision of 30-bit, which is default for default float point precision, and this model uses a half precision point, which is also referred as float precision point of 16. So these are suitable for mobile devices as it requires less memory, as it consumes less memory to operate. So then both of the models were trained and evaluated on the personal computer. Then this raw TensorFlow model I tried to implement on the Jetson Nano. Unfortunately, I couldn't implement on Jetson Nano. The whole system was freezed because it was taking full memory of the Jetson Nano. So I was stuck for a couple of days, like what to do. Then the only solution for this problem was that we have to optimize this raw TensorFlow model to use on Jetson Nano. So in this step, we optimize both of the models, converted into ONNX and TF-TRT format, and then implement it on the Jetson Nano for inferencing. And fortunately, it worked and it gave us some good result. The hardest part of this project was to setting up the whole Jetson environment. It required a lot of setting up the environment, side packages, and also some softwares and backend scripts. So it was very time consuming to do this portion only. Our data set is from Cocoa 2007. Vehicle subclasses and animal subclasses. So these 16 classes were selected randomly. So these 16 classes gave us a total train image of around 80K and validation image of 3K. This portion gives you an idea about the annotations. The default annotation given by MS COCO dataset is not usable for our model. So we had to pre-process the annotations and convert it into Excel format like this. So this is pretty easy to understand. As you can see, this one gives you the information of the image, the width of the image, height of the image, and the channel of the image. And this one is specifically for the ground truth for the bounding boxes or the location of the classes. So as you can see, this is the name of the class, this is the name of the class, this is the name of the class, and this is the information of the position of that class in terms of image. So these were used later on for the calculation of losses and accuracy. So yep, so that's all about the data set. Now this is our model, which is based on MobileNet SSD. It is also pretty simple to understand. The backbone uses a MobileNet version 2. As you can see, the input image size is 300 by 300 by 3. So whatever input you give it to the network, it will be converted into 300 by 300 images. So no problem there. Then this 5 extra convolutional layer was added after this backbone to extract more feature into from the different portions of the pictures, because if there is a picture, you want to focus on the larger object and also smaller objects. So this 5 block gives preference to different sizes of images. So after that a tensor of like 3000 by 29 was extracted from this network, which is passed through the non maximum separation detector to get the desired output. So let's talk a little bit more about non-suppression. What is non-maximum separation? So basically this network would give you multiple bounding boxes prediction for a single object. Like here you can see a dog, then you get a multiple prediction, bounding box prediction. So which one would be the final detection? Okay, so it's pretty easy to understand. Now you see, this is the box with highest probability confidentiality, and these are the boxes which is near the boxes with highest probability. So how do you detect whether which of these 3 blue boxes is appropriate for use, which one should I disregard? So it is pretty simple. A technique of IOU, or in other words intersection over union, is used in this case. So the intersection over union between this blue box and red box will be measured, and if it passes some threshold value, for example the threshold value is 0.5, so if you see this red box and blue box has IOU over 0.5, then we will just disregard these blue boxes. Same thing for these blue boxes. So in this picture, all these 3 blue boxes will have threshold value of IOU more than 0.5, so it will just disregard all these 3 blue boxes. For example, there was a dog at this point, and it will give you another bounding box. So probably the IOU between this red box and this blue box would be less than 0.5. So in that case, we'll keep both of these bounding boxes around these classes. Another technique that was mostly used, so the model was built with 2 different precision mode. So yeah, the first model, the left model, was built with the float point precision of 32-bit, which means that all the data type would be will be consuming 32 bits of memory, register memory for each of those data. And for 62-bit value, it will just take around 60-bit model. It will just take 16-bit of memory for storing the data. So yeah, the 16-bit will obviously be more memory optimized than the 32-bit value, but again this 32-bit value will give you more accurate result than the float 16 value. So you have to compromise between the 2 models. Our training setup is comprised of this thing. So basically the processor is like Core i7 12th gen. The GPU is RTX 3060 with a memory of 6 GB. I used CUDA 11.6, CUDA NN 8.6.0, and TensorFlow GPU version 2.10 to use the GPU with the TensorFlow. For the model with float point precision of 32-bit, I trained for 64 epoch with a batch size of 192 with a learning rate of 0.001. Each epoch took around 4,600 seconds, which is almost about 1.5 hours. So I wanted to keep the batch size as high as possible. But you know, this 32-bit values take more memory than this 16-bit model. As a result, I have gained the batch size of this 16-bit model is higher than these things, which also make the model to train faster. So it took around 1 week to 1 week to train this model and this model, because there were sometimes I started to train the model with like 10 epochs, 12 epoch to check that whether it's converging or not. So yes, I also kind of wasted a lot of time into that thing. So this is the result for the training result. I monitored the for the training purpose, and as you can see, this is the graph that is outputted. So initially, for the 32-bit model, the training loss starts from 22.5 and it's ended up at 6.44, and the validation loss starts with 6.9 and sorry 18.76 and ended up at 6.9 m. So the validation loss start in the initial point, it is lower than the training loss, because it makes sense, as my training data was 80k but my validation data was only 3k. So yeah, training loss would be more than validation loss as the ratio is higher. Same thing happened for 56. It follows the same trends, and it was still reducing after 64 epoch and 120 epoch for the 16-bit model. So I can say that the model is still underfitted. If I could have trained it for more time, I could have gained more accurate result. So this is the result got for mean average precision. Mean average precision is a parameter to, you know, check the validity of a model, which for a real-time object detection model. So mean average precision is the mean of the average precision get for each of these classes. So as you can see, there are 16 classes, and the mean average precision which is plotted against the recall and precision versus precision versus recall. So the curves looks like this. So for the model which was evaluated on the personal computer, it didn't matter whether I use this 32-bit value, which is the left one, and 16-bit model, which is the right one. It didn't matter much, because in most cases the MAP is very close, only a difference of like 1.89. So it is not significant. If I look at the inference speed in terms of FPS, then I can see that the 32-bit model give a average FPS of 14.11, and the model with a 16-bit value give a average speed of like 15.94 fps. So yeah, this floating point conversion from 32-bit to 16-bit kind of affected in the speed, because it also makes sense in case of MAP, as whether you load the 32-bit value or 60-bit value, it doesn't matter much, because it's not about time, it's about the accuracy. So the personal computer is made to load the 32-bit value, but whereas the speed, because it takes less time to load the 16-bit values, so it is obvious that the speed for the 16-bit value is higher than the speed for the 32-bit values. Then yep, the frustrating part, I tried to load the unoptimized TensorFlow model into Jetson Nano, and it didn't work. It was not loaded. The whole system was stopped responding for the 32-bit value. For some reason, the 16-bit value was loaded, but it was giving me like 0.27 frame per second, which is nothing, because training evaluating 3000 images took me around 3 hours to complete. So after like 2 hours, I thought that yeah, just leave it, because it's not a good result, and there is no point of using more time on it. So I left it and started to find some solution how to tackle this problem. So yes, the solution was that you optimize your base TensorFlow model into some other format of model, which can be used by the by the Jetson Nano. So the best solution was to convert the TensorFlow model into NX model. So yes, basically WNX model helps you to optimize the TensorFlow algorithm into some general format, which can also be converted into other format of machine learning, other format of API also. Like for example, you want to convert your TensorFlow model into PyTorch model, then you can convert your Tensor model flow model into ONNX, then you can convert this ONNX to PyTorch model, which acts as a bridge between these two models, which is very good, which is pretty good. So the steps was that you convert your TF model into static protocol buffer data, then you convert that data into ONNX model, then create inferencing for that ONNX model, and then validate using that ONNX model. Now, another idea was to convert that ONNX model into TensorRT model. So TensorRT gives you, it is specifically built for mobile devices, like with NVIDIA platform, which has like Tensor Core inside it. So for NVIDIA Jetson Nano, Jetson Xavier, or AVX, it is optimized for those kind of use. So this is a lightweight model, not TensorFlow Lite, but it's a lightweight model version of TensorFlow, which gives better performance for these mobile devices. So yeah, partial conversion to TensorFlow model was done and checked. So yes, instead of directly loading the model from TensorFlow, we just converted our full model, then load the model and predict the model for the evaluation. Yeah, this is the evaluation result after optimizing the model. So it was still evaluated on personal computer. As you can see now, this time this MAP is affected for both of these floating point values. So you can see that for 16-bit values, the MAP has reduced like 8.51% compared to the around 1% for non-optimized version, because now the network architecture is changed a little bit and optimized. So yeah, it doesn't detect the way it was used to do. The most interesting result is this one. You know, remember the unoptimized speed was like only 14 FPS, but now after optimizing the network, it gives you around 60 FPS for those 3000 validation data. These are the samples. These are the around 3000 samples for the which was validated, and you see this gives you a very good result of 80 FPS. I was very astonished and at the same time very happy to see the result, because I was very much afraid that whether I would be able to get any result or not, but this was good for me and I was happy. After getting this good result, I took this model for Jetson Nano, which is basically a processor is like quad-core ARM A57. The graphics processor is 128 core of NVIDIA Maxwell architecture. It shares the GPU with the 4 GB of installed RAM. The CUDA version was 10.2 and CUDA Nano version was 8.1.0. So the ONNX model was used on Jetson Nano. Now, as we can see that though the personal computer was not affected by this float point conversion, but for Jetson Nano it gave you a huge change. As you can see, for 32-bit value it gave like 28.84, which was pretty close to that 32-bit MAP for the personal PC. But for the 16-bit value, the MAP has dropped 19.52% to 23.05. So it is easily visible that the personal computer is not much affected by this floating point conversion, but this mobile devices like Jetson, which has lower memory, is very much affected by this thing. Then again, but the good news is that your floating precision, the FPS or the speed also increases a lot. As you can see here, the average FPS for the 32-bit was 6, and it increased like 1 FPS for this 16-bit model, which was good. But there are a lot of models already existing which gives better performance this thing, but who knows, it's better, still better, because you have done it by yourself all alone. Yeah, which is good. So if you compare the thing, that you can see that this 7.06 FPS is almost 64 times faster than that 0.275 FPS that was given for the 16-bit model. Now here is some of the results which I found that did not work. There are a lot of results which has some problem with it, so I just chose this 6 pictures randomly. As you can see, this one shows dog. It's kind of like looks a tail of a dog, so I think that if the model is trained for more time, as it is underfitted, that's why it's just telling this one is a dog. This one, yeah, this one is a shark, but obviously for the model still looks like a person who is like who is opening his mouth. So yep, need more training time. This one, yeah, this one looks like a dining table because there is plate, there is a mug. So in general, most of the dining table had these things, the plates and the mugs there. So it pretty much detected that this is a dining table. So if there were more classes like plates and jugs, then obviously it could have said that, yeah, it could have avoided this detecting this thing as a dining table. And you can see there is a person, there is the picture, 3% there. So it detects multiple IOU for one person. Like, yeah, you see this one, there is 2 IOU. So if the IOU threshold is tweaked and matched to some optimized value, this can be avoided. Same thing for this one, but it is pretty much good because it is detecting this 3 horses. And then there is the thing, like the model is already detecting this is a person by using the hand. So the mac box size, like this box size should have been confined to this point, though it detected the value properly, like this person to 3 hands, but the boxes sizes are larger. So yes, bounding boxes sizes has to be also controlled to get better result. So in future, yes, longer training time is required. The converting this model to a full TF-TRT engine will be able to take the FPS to higher level. So I'm currently working on that, and then integrating camera for the Jetson Nano, which I couldn't do yet. So I'll be integrating the camera with Jetson Nano, then use the camera from Jetson Nano to detect objects in real-time format. So that's the future work that I want to do. Oh, this is a demonstration which was just recorded few times back. Oh, I'm not sure whether, yeah, there is. Yep, as you can see, this is the dining table. I don't know why this is dining, because it looks like a dining table. I just recorded it a few times back. So thank you, Zafaria Haidar and Avilash, for being the part of video. So thanks to them. Session is finished. So thank you, everyone. Everyone have a good vacation. Thank you all.